Hello everyone, welcome back to Chemistry 3120. Today's lecture is 7, and we're going to talk about dissolving metal reductions. All right, so we've looked at hydride reducing agents, catalytic reductions. So this will be the last unit on reductions. And what we're going to talk about is some historical examples of using a network of solvated electrons in order to reduce substrates. So sodium in ethanol is one of the oldest forms of one of the oldest forms of reduction. And I'm talking about sodium metal, not sodium ion. And this works well for reducing things like ketones and carbonyls. Another dissolving metal reduction involves lithium, and ammonia is also another type of reduction, and this is also known as the Birch reduction. And this here, it can also be used to reduce carbonyls, but it's often used for aromatic species, and I'll show you that in a minute. Okay, so how does this work? So let's start with the Birch reduction. Okay, so you have lithium, metal, so there's an unpaired, there's an electron there, and if you dissolve this or take that metal and put it in ammonia, what's going to happen at cold temperatures is that that unpaired electron is going to want to lose itself, and it's going to want to pair with other electrons. So what happens is that lithium is very willing to donate the electron, so it becomes lithium plus, and what you end up having is electrons in a solvated network of liquid ammonia. And this is actually like a blue colored solution. And the idea here is that, well, you have this solvated electrons in this network here, and is it possible to therefore add something in order for it to get reduced? If you actually wait too long, or if you actually let this go for a while, what you'll end up getting is you'd start to strip off the hydrogens off the ammonia, and you'll generate H2 plus and H2 minus. So the question is, can we add something right here, maybe a substrate, an organic substrate, before the slow step happens? Can we add something here that can be reduced? So let's take a look at an example of an aromatic compound. And if we take this aromatic compound, treat this with lithium and ammonia, you might say, well, this aromatic compound is very stable. It's aromatic, there's 6 p electrons. It's going to be very difficult to reduce. And while I do agree with you that it's stable and it is aromatic, let's draw some resonance structures of this species here. So we're drawing benzene as I've shown here, but remember that these double bonds can migrate and you can get resonance structure. If we do that for the arrows that I'm showing you here, you're going to generate a positive charge at this carbon. You're going to move the double bond here, and then over here you're going to have a carbanion. Okay, so this is a resonance form of benzene. So if you treat this with lithium and ammonia, remember you now have these solvated electrons in solution. Is it going to be possible to use that or use these electrons in a useful manner? So we have single electrons, and you can see here with this positive charge we can get a single electron going to that positive carbon. Also note that I'm drawing something known as a fishhook arrow. It's not a double-headed arrow. This is a double-headed arrow, which denotes the 2 electrons. A fishhook arrow has a single head on the arrow, and it corresponds to 1 electron moving. So since we're dealing with a single electron, let's move a single electron to that carbocation. If we do that, we're still going to have that negative charge up here, 2 double bonds on adjacent sides, and then here we're going to have a carbon radical. So you have something that looks really nothing like benzene. And however, this carbanion is going to be fairly reactive, and it's going to want to react with whatever it can pick up. So because we have ammonia in solution, it's going to be very, very happy to pick up a proton from ammonia. Here you still have your carbon radical. Radicals don't like to be alone, they don't like to be single electrons, so you're going to have a whole network of electrons here, and you're going to get another electron joining with this electron here to form now a carbanion. And this carbanion can now also pick up a proton from ammonia like we saw up here. So your final product will be something like this. So you lose aromaticity and you do partial reduction of benzene to give you that structure there. So that's sort of an interesting type of reduction, something that you haven't perhaps seen before. So perhaps to finalize this reaction here, this would be your final product. As I mentioned before, Birch reduction is often used for not just benzene, but other types of aromatic compounds. So you'll get a lot of practice with that, with problem set and course pack. But let's look at sodium and ethanol and its ability to reduce carbonyl compounds. Okay, so if you add sodium and ethanol, you're also going to generate a very similar matrix where you have these electrons in solution. And so why don't we start with a ketone, and we apply the same principles that we did with benzene. Let's draw a resonance form of ketone. This is a lot more straightforward. Electrons go up to that oxygen, so you end up generating this as a stable resonance structure. So where electrons can come in is that they can now add to this carbocation as I've shown here. So here's an electron. You're going to get insertion or addition to generate this here, which is called a ketyl keto radical. I'll just add to the title, reduction of carbonyl compounds. Just so it's clear, using sodium in ethanol. So we have ethanol present. And like we saw with the birch, you're going to transfer a proton to the negative carbanion. We're going to do the same type of thing, except it's now going to be oxygen. So you now generate this alcohol. You still have a keto radical. And so what's going to happen next? Remember, you have free electrons in solution. So this is another electron's going to add, so it can become paired. And now you're going to generate this keto anion, this carbanion. And then this negative anion can now pick up a proton from ethanol. To generate this form, which is the reduced form of the ketone. Okay, so this would be a very similar product, or the same product that you would get with something like sodium borohydride, for example. However, the mechanism by which we do so is different. Now, if you're trying to generate this product, you might just want to use sodium borohydride. Using sodium in ethanol, it's going to be a much more complex procedure, technically speaking. But I'll show you an advantage of using this method if you're trying to generate, maybe not this species, but a different type of species. So if you actually reduce a reduction of benzophenone, benzophenone is a ketone that looks like this. Reduction of benzophenone. Can give you two different products, actually. So if you actually do this reaction, you're going to generate two products. One is the reduced form, which would be the alcohol, like we've seen up there. So let's draw that out. And the other one is actually this diol that looks like this. Okay, so it almost looks like a dimer of these two compounds coming together. So this is obviously a very different product from this one shown. And how can we account for this product formation? Because it's sure, it is a reduction, but you form a new carbon-carbon bond. So the way that this functions is that during this initial phase here, let's draw out your resonance structure. I'll just abbreviate phenyl groups so I don't have to draw them out each time. You get your electron transfer to this carbocation. And you form this keto radical. Okay, just like we've done up there. So to generate this product here, you'd follow the same mechanism as I've shown up there. However, what you can see in this example is that in order to form that carbon-carbon bond, radicals don't like to be unpaired. So a new carbon-carbon bond formed between these two radicals. I'm just showing you two fishhook arrows coming together to form a new sigma bond. And what that will do is that will generate carbon-carbon bond, as I'm showing you here, like this. And then the rest is fairly straightforward. You just simply protonate one of them at a time. If if you do them at the same time, it implies, or it therefore suggests mechanistically that they have to happen at the exact same time, which we know is not true. So make sure you pick one of them and then just protonate one and then do the other to give you the final product. Okay, so the way that we can generate these two different products from the same starting material is as shown through this mechanism. If you wanted to make exclusively this, or make that as your major product, how could you control the reaction? Okay, so if desired as major product, how can we try to enable this carbon-carbon bond reaction to happen? Well, think about concentration. What we can do is we can try to do a reaction that's very concentrated, so we have the ketyl radical in high concentration. So don't do this under dilute conditions. You want to keep this concentration high. There's an arrow going up, high. Okay, that's if you want this. If you want this as your major product, keep the ketyl radical keep that low. So add lots of solvents so it's dilute, so that you therefore promote reduction and then a free electron from the system pairing up to form a carbanion. Okay, so these are dissolving metal reductions, and that concludes our unit on reduction in general. And what we're going to talk about next time is oxidations. So see you then.